Hello everyone, so welcome to second lecture of week 4. So in this week we are talking about recurrent neural networks architecture. In the last lecture I talked about the language modeling through recurrent neural networks, and in this lecture I'll discuss about further applications of RNN. So we will talk about applications in text generation, sequence labeling, and text classification. So these are the topics that we'll be covering in this lecture, RNNs for these various applications. Now, just a quick recap. What did we discuss about recurrent neural networks in language modeling? So what would you do? So you have some input that you are feeding into the model. So suppose these are the embeddings of the words. So x1, x2, x3, x4. They denote the embeddings of the input words in the sequence. And in recurrent neural network, what you do, you have some initial hidden state h0, and you keep on updating it, right, using the new information that you are getting. So as soon as you get x1, you update it to h1 by using the previous hidden state and the current input, and so on. You update when you get x2, you update it to h2, and so on. And you typically use the final representation of the sequence, that is your h4, to make the prediction. In this case, the prediction is what is the next word in the sequence. So we also discussed about this part that you can use another matrix V that will project this h dimension to the vocabulary dimension, and then you will apply softmax to the prediction. And the advantages that we saw is that now it does not matter how long your input is. You can process any length of input by this, and the model size remains the same, that is W, U, and V are the parameters. And you can use you can use information from any steps back, right? And all these weights are shared across the steps. You don't have separate U matrices, separate W matrices. The same U matrix that is there everywhere. And of course, this creates a little bit complication in how you compute the loss. I mean, how do you backpropagate the loss? So loss is very standard, the cross entropy, but the same loss would have component in the U matrix at multiple time steps. So you would have to find out the loss that you're computing at this time point. How does that contribute to, what is the contribution of this W matrix here, also this W matrix here, and you have to add all these contributions. Same way you will do for all the matrices. So this becomes a bit more complex, the deriving this gradient of the loss with respect to each parameter, but this is called backpropagation through time, BPTT. Okay. Now let's come to the applications that we are discussing in this lecture. So how do you generate text with RNN language model? So now you already have the basic idea about how would you do this. So this is very similar to how you do in a general language model, even n-gram language model. Okay. So you have a probability distribution, and from the distribution you have to generate a word. Use that word to again sample another word in the next time step. So you can actually use this for language generation, and this actually implies that you can use it for any generation task like dialogue, machine translation, etc. We will discuss these in bit more detail in the next lecture, that how do you use RNNs for different sequence to sequence problems. But today we will talk about just generation and other paradigms. Now what language model can do, it can incrementally generate words, right? So it will not generate all the words together, it will generate one word at a time, and this would again go into the conditioning to generate the next word, right? And this is why it is called an auto-regressive generation. So you don't just generate the entire sentence at a go, you have to generate one word, use that as an additional context to generate the next word, and so on. So it is auto-regressive generation, and that's what we will typically use in various architectures, including RNNs, transformers, and so on. So how do you do auto-regressive generation with RNN? Right. So what it means is that your parameters are already fixed and they are frozen. You are not changing your parameters. So all the matrices U, V, W have already been trained, and you are sufficiently confident in the parameters. Now you are ready to start generating. Right? Now, what would you do to generate? See, suppose you are not given any input. You are just told now you generate some text. So you have to start your RNN from some input, right? So what we do, we start with this beginning of sentence token, BOS token. So there are various ways you can write this. So beginning of sentence token. So this will be the input. So this becomes your first input. And now you see your, and you have to have some way in which you can define your H naught. Let's say you have some all 0 initializations, right? So this is just all 0. You can do another kind of initialization. Let's say all 0 initialization. So then what you would do, you would have this matrix U and matrix W. Use that to compute hidden state at time 1. These are already trained. So you would, it's deterministic, right? What will be H1? And then you use H1, apply the matrix V, and project it to the entire vocabulary. You would have a softmax here. So you get a distribution. And from this distribution, let's say I take the word which has the highest probability. Right? So let's say the word D has the highest probability, say 0.6. So that means I have generated the word D, right? If I have taken the word with the highest probability. Then I'll take this word and put it as the input for the next step. And what it means, I'll take the embedding. Like beginning of sentence will have an embedding. So I'll feed the embedding of this. Similarly, I'll feed the embedding for D. And again, I have the matrix W. I have the previous H1 computed. I'll have the matrix U, and I'll apply the forward propagation to obtain H2. And this will get multiplied with V matrix. Again, I'll get another probability distribution after softmax. And take, say the word is weather. So I'll generate the word weather and use it also as the next token. It's embedding. And I keep on doing that until I have some end of sentence condition, which may be either the end of sentence token is generated, or because you don't want it to generate forever, you may also have a constraint that I will stop whenever it has generated at least, generated say 15 words. I don't want to go beyond that. So whenever it has generated 15 words, even if I do not get an end of sentence token, I can stop. So you can have some termination condition. Okay. So this is how this generation is done. Now question for you is, the way I have described it, if you generate like that, how many different sentences can you actually generate? Right? So think over it. So parameters are frozen. There is no randomness. You are initializing even H0 as some all 0 or some fixed initialization. So because everything is deterministic already, so that means this distribution will be deterministic and the highest probability will also be deterministic. So henceforth everything else will be the same. So that means in this way, whatever I have described here, you will only generate one sentence. So this description will only generate only one sentence, right? But suppose you want to generate multiple types of sentence, what you will have to do? So you can play with various things. Say you can do different H naught, you can give different initialization. But even then, what you can play is the sampling process. That is typically how people generally generate diverse sentences. So what do you mean by playing with sampling process? So from the distribution, do not always sample the word with the highest probability, but you can do a random sampling, as per the probability, right? So that means this word the, if it is probability 0.6, it will still have a probability 0.6 to be sampled, but other words will also get a chance, right? And we had described this when we talked about the language model generation, right? The n-gram language model generation. It's the same process. So what we would do, we feed the sentence S through its embedding, we get the hidden state H1, we apply softmax, we get a distribution, and then from the distribution we sample a word, right? We just don't take the word with the highest probability, but we sample a word. And suppose you sample so, you feed its embedding and so on. And you continue until at some point you have generated the end of sentence token. So this is the autoregressive generation that you do with RNN, and this will be very handy to understand how you use RNNs for any sequence-to-sequence task like machine translation, dialogues, and so on. We would actually repeat the same process. But now what will happen, you would have a separate conditioning. So you would have some additional input to the first hidden state. Right? So you will have some conditioning from the left, right? Because you had some extra input for which you want to generate. Right now there was no input. You were just generating once your parameters are frozen. Okay. So this is a nice picture to tell like RNNs are very versatile. They can be used across various applications. So we talked about language modeling, that you can generate the next word using RNNs. Next we will discuss in this lecture sequence labeling, that this paradigm we talked about, that you can, for each word you have one output. Yes, for each word you have an output. So there is a one-to-one match between the input and the output length. Then there is a sequence classification paradigm where for the entire sequence we have one output, say the class text classification. And you have sequence to sequence paradigm where the number of words in the input and number of words in the output can vary. So you don't have a one-to-one correspondence. So you have an input, so you have a sequence, from there you generate another sequence. So it's not like you're labeling each word, you're not generating one token per word, no. Given the sequence, you're generating another sequence, right? So this we will cover in the next lecture. Okay. So let's understand these paradigms and how do you do sequence labeling through RNN, how do you do sequence classification through RNN. So what is sequence labeling again? So what is the paradigm? So you have a small fixed set of labels, right? So it can be say part of speech tags that may be say 45, 50 as per the tag set. And you want to label each sequence, each element of the sequence with one of these. Okay. So your input would be, so you are giving the input as a sequence of words and you will give the embeddings for each word. That is your input. And output will be typically tag probabilities, right? So from there you can do sampling. Typically in this case you will take the maximum probability generally. So output will be tag probabilities, from which you will typically take the word with the tag with the highest probability. Right? So that is what you are looking for. So how do I achieve that through RNN? Now you can just it's not very difficult to visualize how you would achieve this through RNN, right? So what you will do again, so let's say you are doing part of speech tagging, where for each word you have one particular part of speech tag. So what I will do, I'll feed the sequence, word sequence through their embeddings. So they become the input x1, x2, x3, x4, x5, and this we are not showing any connection. This is analogous to, this is very similar to saying that your initial hidden state is all zeros. So that means no input comes from that, right? So you apply this matrix W here, and you get the hidden state H1. You apply the matrix V to this, and you get a distribution, probability distribution over the entire text set, right? And from there, let's say you select the argmax. So you take the maximum probability tag say NNP, generate NNP, and then again, and you don't feed now, okay, this word, because you have the entire sequence already there. So you just obtain this word, right? Then the next word, you will have this hidden state giving you input to get your next hidden state. Again, get the probability distribution, take the argmax, modal verb, and so on. You will generate the entire sequence, tag sequence for your word sequence. So you are labeling your entire input sequence with the tag sequence, right? So again, whenever I describe an architecture or explain, you have to realize there are two phases. Of course, there is a training phase, there is a inference phase. In the training phase, your model parameters are yet to be trained. So what you have to understand is that where is the training signal coming from? So how would you train your parameters? What is your loss function? In this case, the loss function can be simply cross entropy loss, because you are having a probability distribution, you know the ground truth tag. So you can take the minus log probability of the ground truth tag, right? So here you can do just cross entropy loss. And then there is second phase is the inference phase. In the inference phase, your model parameters are already trained. You are giving a new sequence, which may be seen, it may be unseen, but the use case is typically you have an unseen sequence. Now because everything is trained, you will be able to apply those parameters and get a distribution, and then to give an output you will take the argmax over this distribution. So what is being shown in this slide is the inference part, where you simply take argmax, right, because you are wanting to create an output. So here parameters are already frozen. Okay. So this slide talks about the inference phase. So now let me talk about another application through sequence labeling. We talked about this briefly earlier, but here I'll talk about this in a bit more detail. This is named entity recognition problem. Right? So what are named entities? Right? So typically something that you can refer as proper name, but this can actually vary across domains. So this has a lot of application in biomedical domain, where you want to find out the genes, proteins from literature and other documents. This has application in financial document, where you want to find out the different tag sets, so XBRL tagging. Application in legal domain, where you find out who are the lawyers, who are the different parties that are involved in this case, and so on. Right? So you may define the entity tags separately as per your application, but in general you can say, for example, general named entities are person, location, organization, and geopolitical entity. They are typically very generic named entities. So example of person is Marie Curie, location New York City, organization like Stanford University, and geopolitical entity like Boulder, Colorado. Right. So one thing that is different about NER is that there would be some like multi-word entities in general. Of course, they can be one-word entity also. And we will see in the literature, I mean, this has been extended to various things that are not exactly entities, but you still use the NER tags for that, like times, dates, prices. You still use some NER tags for those. So what is the task? That first of all, you will just be given a sequence of words. You have to find what is the span in the sequence that constitutes proper names. Okay, and there will be more than one spans, right? So you are given a sequence of word W1, W2 to Wn. It may happen some Wi, Wi plus 1 is a named entity, and it will also have a particular tag. Say this is a person, and say W1 or W2, W3, W4 is another named entity, and let's say this is organization, and say Wn is also named entity, that is so geopolitical entity. And others are not named entity. So this is, you will just call it it's not a named entity. So how do you actually represent this information? How do you actually extract this information? This is different from Parto switch tagging, where you just had one tag per word. Now you have to find a span inside the sequence, and for the span you have to give a tag, right? So this is a bit more complicated, and in general this is like a structured prediction problem, because you have to find out what is the span, what is the tag for each span. It's not fitting directly into sequence labeling, but we will see what is the trick typically used, so that we can still use sequence labeling for solving or for applying to this problem. Okay, so this is one example. Like you can see, there may be multiple words, they can be a single word, right? Multiple words, they have one tag, and in a sentence there can be more than one. One single tag can occur more than one times, right? So here you have multiple locations. It's not that in a single sentence you will have only one location tag. You may have multiple tags of the same type. So it's an interesting problem. And why this is important? Because you need NER across different applications. For example, you want to find sentiment of the customers towards a particular company or person. Typically it is handled through aspect-based sentiment analysis. Also target-based sentiment analysis. There are various terms for these. So you have to find out what are the named entities towards with a consumer has expressed sentiment. You have to again use this NER tags for finding that entity. Question answering, you may have questions about an entity, and information extraction, where you want to extract facts about different entities, right? So all of these places you would need an NER. And why is this hard? As we discussed, I mean, in pause tagging you don't have any segmentation problem, because each word will have one tag. It's very standard. But in NER you will have to find what are the segments that will have the tag, right? What are the segments? So you may have, as we saw, there may be 3 words together that are given one tag, and the same word may be applied, may be given multiple tags in different context, right? That's the general problem in NLP, the ambiguity part. Washington can be person, organization, location, geopolitical entity, as per the context, right? So it's not that given a name you will have only one tag associated with that. So there is also an ambiguity there. So now, of course, one can say that, yeah, I'll try to convert it to part of speech tagging, where what I will do for each word, let's say I have a 3-word phrase, WI, WI plus 1, WI plus 2. I'll call them all. If they are, if this together is location, I'll simply tag that as location. And in my output, whenever there are consecutive words that are given the same tag, I combine that span and say, okay, this whole span WI plus 2 is together location. Now that can be one way of dealing with this problem, right? But the issue with this is, I can't distinguish this from another situation where you may have WI plus 1, WI plus 2, where WI is a location, a single word span, and WI plus 1, WI plus 2 is again a location, a span of 2 words, right? So there are 2 different locations. I can't distinguish it from the another scenario where 3 words together is a location, if I use this scheme. That's why people don't go for this, that you use the tag per word and then combine it at the end. Typically this is not used. Okay, so what is the trick to avoid this problem? So we use something called BIO tagging. Okay, so this is a way in which we can turn this structure prediction problem in general into a sequence labeling problem like pause tagging with one label per word. Okay, so let's take this example. Right? So Jane Villanueva of United, a unit of United Airlines Holding, said the fare applies to the Chicago route, and you have this 2 words as a person and these 3 words as an organization. Now how would I use this BIO tagging? So what is the idea? So BIO means you have beginning of a tag, intermediate of a tag or inside of a tag, and outside. Okay, so any word that is not tagged is anyway given O, that is easy. So off will be given O, a unit off, they will be given O, and yeah, not all words are here. Discussed, they will all be given O. But Chicago is one word, so you always start with B of tag, so beginning of location, it just ends there. But if you have 2 words like Jane Villanueva, you will have beginning of person and inside of person, right? So that means at the end, how will you process this output? You will say starting from B person, and wherever it is ending with I of that tag, you will call it a single named entity tag, right? Similarly here, B of organization, they all are I of organization, as long as it goes, right? So this, you can easily distinguish between 2 scenarios where you have B location for one word, then again B location and I location. That means there are 2 different named entities. So this is one, and this is the second named entity. Versus if you have B location, I location. So this is like a single named entity, right? So you can now distinguish it. And then you have only one tag per token, right? So that means if you are using BIO tagging, so beginning, inside and outside, so you will have a little more number of tags that you already had. Let's say you had n entity types, right? This person, organization. So how many tags you will have finally for your problem? So because for each of these you will use beginning and inside, you have 2n, B tags, ni tags, and 1 O tag. So you have 2n plus 1. So this can be handy when you're solving problems regarding, right? I mean, if you have given say 4 different entity types, how many actual tags are there? There are 9 tags in the BIO scheme, right? So your output layer would have dimensions according to this, right? Okay. So you can try the simple problem that suppose you are using a 300 dimensional word embeddings to represent each word, and you have 50 dimensional hidden vector. So this is dimension 50, and you have 50 part of speech tag. That means the output dimension is 50. So what will be the number of parameters excluding bias terms, right? Now you may be, this may be an easy question for you. So you can say, okay, I have this matrix W, U and V. W dimension are 300 into 50, U is 50 cross 50 and V is also 50 cross 50 because both this and this are 50, right? So you add all this, so it will be like 300 plus 50 plus 50 times 50, that many parameters. So 400 into 50, so this will be 20,000. So 20,000 parameters, right? So that will be the parameters excluding bias terms. Now similarly, now if I give a slightly different problem saying, suppose you are using 300 dimension word embedding, right? 50 dimensional hidden vector, same, and you have 5 NER tags, right? So 5 distinct entity tags. So 5 distinct entity tags. And you are using the BIO tagging scheme. What will be the number of parameters? So what will change now? So your input is again 300 dimension. Your hidden is 50 dimension. Your output layer, what is the dimension of the output layer? How many probabilities you will compute? How many classes would you have? So you have 5 NER tags. So each BNI for each of these plus an outside. So there will be 11, right? So accordingly you can compute. So this will come out to be 300 plus 50 plus 11 times 50. Right? That will be the number of parameters that you will have in this scenario. Okay. Now coming to the last application, that is how do we use RNNs for text classification? I mean last application for this lecture. So consider this example. Overall I enjoyed the movie a lot. I want to find the sentiment for this, and typically sentiment you may have 3 classes: positive, negative, neutral. Now how do I do classification, right? So this is a very similar problem to what we discussed briefly in the last lecture also. That is, you are given an input sequence and you want to encode it, and once you have encoded the sequence, then it is just like the input representation for the entire sequence, and you can apply any network architecture to do the prediction, right? So I just have to see how to encode it, and RNNs are actually doing that. So I can apply an RNN over this entire sequence and I can get encoding from that hidden representations. How exactly? So what I can do, I can feed this through an RNN, so through the embeddings. So I am feeding the embeddings for overall, embeddings for I and so on through this matrix W, and I have the hidden states being computed by using U and W, right, until I get to 1, 2, 3, 4, 5, 6, 7, H7, right. And this H7 captures all the context of the sentence, right. So H7 captures the entire context. So I can say now this becomes my sentence encoding, and I can apply another matrix on top of that to do the final prediction, right. So to take it to 3 dimension, that is positive, negative, neutral, and I do softmax and all, right. So I can do the training accordingly, I can do the inference accordingly. So this is the basic way, just use the final hidden state. There are other ways of doing that. So usually what you can do, because now see as such H7 captures all the information, but still is the same dimension where you have to keep on adding more and more information. So because you have anyway access to all the hidden state, why don't I use all the information? So typically what you can do, you can actually take all the hidden states and take maybe the element wise max. So suppose they have D dimension, they are dimension 1 to D, and each hidden state has some value. You can take the max among all the hidden state, H1 to H7. So dimension 1 to D, suppose this is minus 0.1, but here it is 0.9, everywhere else it is less than 0.9, so I will just take this. But for some other dimension, suppose this value is high, so I can take this, right. Or you can just take mean of all hidden states. I can just take an average of all hidden states. They are very similar to like mean pooling and max pooling in CNN architecture. So I can do that and create a sentence encoding that takes all the hidden states into account and use that to further do the classification, right. So I can apply another V matrix that we had, and that will take to say 3 classes. If I am doing classification for 3 classes, and of course if you are doing for more classes, you can modify this, right. Sometimes you also apply a bidirectional RNN. Like, what is the motivation? So this is how you will do for another sentence. The movie was terribly exciting. So I'll go from left to right. I keep on getting embedding, and I take the element wise mean or something, right? That's what we described. So what will happen now? See, because you are only getting the left context at this point, because terribly in general is a negative sentiment. So this hidden state will be more negative, right? This will have a more negative sentiment representation. Right? So this would have more negative sentence representation, right? Because this hidden state captures information up to terribly. Right? So this contextual representation will be more like negative. And why? Because it's only containing information from the left. But if you knew that the right word is exciting, this would have turned into a positive sentiment, right? That's what the author, the writer would have wanted. The terribly exciting, terribly is more like a positive sense. So this modifies the meaning. So exciting modifies the meaning of the word terribly from negative to positive. So this I could have got if I also had the information from the right to left. Okay. But RNN, we are only going from left to right. How do I get information from right to left? That's where the bidirectional RNNs come into picture, that you can actually capture information from both left to right and right to left. How exactly? So idea is very, very simple. So you are anyway doing this RNN, call it a forward RNN. So you are going from x1 to xt, right, up to a certain point of time. Similarly, you apply a backward RNN that will go from the last word backwards up to xt. So you are going from x1 to xt using a forward RNN, and you are going from xn to xt using a backward RNN. And you are getting hidden state for the tth word. So one is ht in forward direction, this is backward, and ht in the forward direction. So you have two different representation from two different RNNs. You just combine the representation, like concatenate them. And this becomes the representation that captures information both from left and from right, and use that to do the prediction. I mean, use that to do whatever else you want to do, like taking the mean of the sentences. You can use it for NER also for doing the prediction at that point. So that's the interesting part about bidirectional RNNs. They can combine two independent RNNs, one where input is processed from left to right, forward RNN, another where it's processed from right to left, backward RNN. So what happens, they don't share the parameters, so you can work out the number of parameters actually change, they become roughly doubled, right? So you can work it out. So because your matrix U, V and W will be different for the forward and backward, and actually what will happen, your V matrix would be shared, right, but the input will change, because now in V matrix you are getting double the 2h dimension input, and this 2h dimension input will go to your final output, right. So you will have 2h times the output parameters, 2h times V. So you will see in fact your parameters double by using bidirectionality, because you are not sharing the parameters across forward and backward, right. But this is a nice way in which you can combine information from both left to right and right to left. So this is a pictorial representation that from forward RNN I get this H1 forward, H2 forward, up to 3, 4, 5, 6, H6 forward, and from backward I'll get start from H6 backward up to H1 backward, and then again concatenate the forward and the backward to make the final representation, right. And this final representation is what is your contextual representation that takes care of both left and right context, and use that for whatever application. So you can use it for sequence labeling, you can use it for sequence classification, and this is very popular using bidirectional RNNs. Okay. So yeah, so this ends this particular lecture. So you can again refer to chapter 8 of our SLP3 book. We will go next and talk about more application in sequence to sequence labeling and beyond. So thank you.